Hello everybody. So we just took our quiz on using VT graphs to solve kinematics problems, and some of you guys nailed it. Some of you guys are doing all the steps perfectly and neatly and cleanly, and you're getting great results. Others of you are very close and made a couple silly mistakes. We can fix that. Some of you still, I feel like, are not buying into this, and I think you may still be trying to memorize formulas or just kind of do random math. And it's really crucial that you guys can follow the process. I want you to understand this and not just memorize, So let's go through this a little bit together. I've got a few sample problems I can do, and you can stop and you can rewind and you can pause and play things over again if you want. So let's just dive in. I'm going to put a few out there. Here's the first of a few. Here's a sheet that I will link on the Canvas page. Okay, so steps in order. Let's write down what the problem tells us. A car initially traveling at 24 meters per second. Oh, so we know our initial velocity equals 24 meters per second. Slams on the brakes and moves forward 196 meters. What does that describe? That is your displacement, and that's 196 meters. And this is before coming to a halt. A halt means that the final velocity equals 0. We want to know the magnitude of the car's deceleration, which is just acceleration. We have an answer that it should come out to be. If we do everything right, let's see if that works out. All right, so there's first step, write everything down. Second step is where some of you guys are fighting me, and you really do need to know how to do this. And that is to make a VT graph. Velocity over here, time there. We're starting, our initial velocity is 24 meters per second, so that's up here. It's not 0, it's above 0. And then it slows down to 0. So you got this sort of situation going on. All right, so there's our graph, because it does end up at 0 and it starts at 24 meters per second. Next step, if you were to find the area of this, because the area of a VT graph gives you displacement, what formula would you use? Well, when I'm looking at this, that's a triangle. So that means it's 1/2 base times height, or height times base. So I'm going to go 1/2 our height, which is our change in velocity. So I'm just going to call that delta V. And then we're going to multiply that by the base, which is the change in time. Beauty. We've got an equation we may be able to use. Now we're trying to find acceleration. This isn't going to give us that. But hey, wait a minute. There's 1, 2, 3 variables. Do I know delta x? I do. So we know that. Do I know delta v? Hey, I do. It's 0 minus 24, so I know this. Do I know t? I don't. But if I know 2 of these 3 variables, I can find the time. So I'm going to rearrange that. And I'm going to get 2 delta x over delta v. That's some algebra. If you're having trouble with the algebra, come see me or your math teacher. So here, t is going to be 2 times 196 meters, because that's our displacement. And we're going to divide that by the velocity, which is negative. We'll keep it positive. For changes in time, you can keep it positive. It gets confusing when you start messing with that stuff. So divided by 24 meters per second. So I'm going to bring this down to the next page a little bit. So we know the time equals whatever that is. You can do some quick math. And that is 16.3 seconds. All right, does that get us anywhere closer to our answer? We're not looking for time, we're looking for acceleration. So let's think about what we know about acceleration. We have a formula for acceleration. Matter of fact, it's a definition. It's the change in velocity divided by the change in time. Do I know enough of that information? Sure, I have the change in velocity, which is negative 24 meters per second. And I want to divide it by the time, which in this case, the time was 16.3 seconds. Do some quick math. And you get 1.47. The units are meters per second, second squared. And because that's a negative 24, that's a negative 1.47 meters per second squared. You got to ask yourself, does that make sense? Well, it's slowing down. So yeah, this says it's losing 1.47 meters per second every second. That checks out. Don't forget that important question. Does it make sense? And then, hey, check it out. That's what the problem told us the answer should be. So it looks like we're in good shape. All right, there's one. I'm going to do more. I'll be right with you. Here's another problem that shows just a slightly different type of situation. And, you know, same process, of course, all the way through, but just slightly different graph. All right, so a bike that is coasting down a steep hill increases its speed from 8 meters per second. Hey, that sounds like an initial velocity of 8 meters per second. And it goes to 14 meters per second. So final velocity is 14 meters per second. The length of the hill is 55 meters. So that means their displacement is 55 meters. How much time, so we're looking for time, passes during the descent? That's, it should work out to be 5 seconds. Let's find out. Okay, so we've got everything listed. Hey, what can we do with that? Those things we can say that the change in velocity is from 8 to 14. Hey, that's 6 meters per second. That's how much it changes. Notice there's a big difference between just saying V1, VF, and delta V. This is the change in velocity. That matters. All right, step 2, you got to get on board, people. VT graph. Velocity, time. This one starts not at 0, it starts at 8. So let's put that there. And then it increases to 14. So let's put an 8 there. You don't need to put numbers, but sometimes it helps visualize things. And this is the end of the time. All right, there's a good looking graph. And we're going to get some equations from this. How do we do it? Well, once again, the area under it. So hopefully by now you've recognized we can just turn that into a rectangle and a triangle. The area for the bottom here would be the initial velocity times the time. And the area of the top would be, it's a triangle, so it's 1/2 the change in the velocity, because that's the height of this triangle, times the time, which is the base of this triangle. So because we know the area under a VT graph equals displacement, our formula for the displacement would be all the stuff added together. V naught T, you're not working, pen, plus 1/2 change in velocity times time. All right, so we got to ask ourselves, is this going to be useful to us? What do we know? Well, we know delta x, we know our displacement, we know v naught, we know delta v. That leaves us with only one variable. That's good. So we can use this guy. So let's go ahead and use it. So you can say delta x equals, I'm going to redistribute, or pull that t out of there. So it's v naught plus 1/2 delta v, all of that times t. Just undistributed the t there. And then you can do what you want to do from here. I think it might be easier to pop the numbers in. We know it's 55 meters per second is the change. I'm sorry, 55 meters rather is the displacement. Let's get rid of that per second. Equals v initial, which is 8 meters per second, plus 1/2 of the change. If the change is 6 meters per second, half of that would be 3 meters per second, all times t. So we know that 55 meters equals 11 meters per second times t. Let's divide that 11 meters per second out of there. 11 meters, and I'm going to put the per second up here. They're gone, and end up with t equals 5 seconds. And check it out. That's what it should have been. Okay, here's one last problem we're going to squeeze in this video. Let's get into it. So we know that a car's brakes can decelerate. Hey, acceleration. If it's decelerating, it's negative 8.0 meters per second squared. And its minimum stopping distance, so we want a final velocity equals 0. That's what stopping means. And we also want the stopping distance, so we want delta x equals, of a car that is initially traveling initial velocity of 20 meters per second. All right, so We know acceleration. Hey, if I know the final and the initial velocity, I can also find change in velocity, which is negative 20 meters per second. Why negative? Because it's going from 20 to 0. 0, and it's always final minus initial. 0 minus 20. You're losing that many meters per second. That's what you want to do. All right, before I just dive into the VT graph, I always like to see, is there anything I can do with this information? If I know the change in velocity and the acceleration, what can I do with that? Oh yeah, remember this? That acceleration equals the change in velocity over time. If I know that, I can find the time. So I know the time equals delta V over A. So here you're going to have a negative 20 meters per second. That's our change in velocity, divided by our acceleration. Or am I? Let me do this, machine. Here you go. Divided by our negative 8 meters per second squared. Get rid of some units there. Meters are gone, meters are gone. One of the seconds is gone, one of the seconds is gone. It's in seconds. Hey, it looks like I've got it set up properly. So I'll move forward with my life. And I've got negative 20 divided by negative 8. You crunch numbers on that. That ends up being 2.5 seconds. And notice the negatives cancel. So now I've got a new piece of information to add to my list. All right, next up, VT graph. VT. This thing starts with an initial velocity that's not 0. It's up here. It's 20. It's going down to 0. That's a triangle. So we know that the area, which is delta x, will have to equal 1/2 times the change in velocity times the time. We could do the one with acceleration. We could do delta x equals 1/2 at squared. Why? Because remember, delta v is at. You pop that in for that, it becomes at squared. Either one of these will work. Which one do you want to go with? I'm going to take the easier of the two, which I believe is the top one, because there's no squaring involved. So we know delta x equals 1/2 times the change in velocity, which is 20 meters per second, times the time, which is 2.5 seconds. And if I crunch the numbers there, 1/2 times 20 is 10, times 2.5 is 25 seconds meters. And lo and behold, hey, that's what we're supposed to have gotten. All right, I hope this is helpful, you guys. Just remember, line up what you know, draw a VT graph, get the equation, plug and chug. All right, I hope you're well. Come see me if you need help.